This is Donna Nelson at the University of Oklahoma, filming a lecture for my organic chemistry class. And this is going to be the first lecture for Chapter 20, Carboxylic acids and their derivatives. And we're using David Klein's textbook. So let's look at what we're going to cover in this chapter. So in this chapter, we're going to film 5 lectures. So here's the first one. That's the one we're doing now. Introduction to carboxylic acids, nomenclature, structure and properties, preparation, and some reactions of carboxylic acids. Then we'll look at the, I'm not going to list all of these, the remaining sections starting in the next lectures. So let's look at, first, we'll look at the introduction to carboxylic acids. So carboxylic acids, they're abundant in nature. They're extremely important compounds. Here you see many examples. Acetic acid, notice you have 2 carbons in the chain, 4 carbons in the chain. Butanoic acid, hexanoic acid, lactic acid, and acetylsalic acid. And you can see these other 2. So there are a wide variety of carboxylic acids. The U.S. produces over 2.5 million tons of acetic acid per year. And that can be easily converted to vinyl acetate, which is used in paints and adhesives. They're very common molecules. Monocarboxylic acids are named using the suffix oic acid. So for carbons, butanoic acid. So 1, 2, 3, 4, 5. So this molecule, which has substituents, and you can see it's a pentanoic acid, and it has a hydroxyl group at the 5 position and 2 methyls at the 4 position. 5-hydroxy, 4,4-dimethyl pentanoic acid. Notice that the carboxylic acid functional group has a higher priority than alcohols. And so the highest priority functional group is always put at the 1 carbon. So if you'll think about it, you'll realize that in this course we have sort of covered the functional groups in a general order of their priority in nomenclature. So the alkyl halides came first, and they have the lowest priority. It's the same priority as alkyl groups. And so as we have gone through this, you've gone to gradually higher priority functional groups. And so if you think about the order in which we've covered these, you'll realize that that's an approximate order of their functional groups. I might mention that amines will be covered in Chapter 22, and that will be an exception to what I just said, because amines have a very low priority in nomenclature, around the same order as alcohols. So this is going to be approximately true through the carboxylic acids and their derivatives. When the carboxylic acid group is attached to a ring, it's named as the alkane carboxylic acid cyclohexane carboxylic acid. So here's the cyclohexane. And also there are a lot of common names: formic acid, acetic acid, propionic acid, butyric acid, benzoic acid is a very common one, and this is one that is often mistaken. So you might want to take a good look at benzoic acid. This is the one in which the carboxylic acid is on a carbon that is directly attached to the benzene ring. Dicarboxylic acids are named with the suffix dioic acid. So here you can see the two carboxylic acid functional groups, and this is pentane, 1, 2, 3, 4, 5, pentane dioic acid. So the carbon in the carboxylic acid is counted when you're counting the number of carbons in the chain. So here are common names: oxalic acid, malonic acid, succinic acid, glutaric acid. I don't know that it is required or necessary for you to memorize the names of all these common names for all of these acids. It is much more important for you to learn the IUPAC nomenclature. You're more likely to see that, and also all the countries in the world, the chemical community generally, is trying to switch over to IUPAC nomenclature. Recall the carbonyl has trigonal planar geometry, just as the aldehydes and ketones do. The acid moiety is capable of strong hydrogen bonding. So for the two molecules, carboxylic acid can be either or both simultaneously a proton donor and also an electron pair donor. And because of this multiple hydrogen bonding, which is quite strong, carboxylic acids have higher boiling points than alcohols and than you might expect. Carboxylic acids are weak, but for organic compounds, they're rather strong. But in the broad scheme of things, comparing them, say, to sulfuric acid, they're weak acids. They will exist as a carboxylate salt in the presence of a base. The base will pluck off a proton easily, and you will have the carboxylate salt. Carboxylate ions in nomenclature end in O8. So benzoic acid has the suffix benzoate. So this is named as sodium benzoate. Benzoate, the derivative of the benzoic acid. Carboxylic acids only dissociate slightly. They are, again, weak acids. And the pH of most carboxylic acids is between 4 and 5. Although, as you see here, as I said, that is rather strong for organic compounds. Remember, the pH of, say, ethane is down around 50. So this is quite strong for organic compounds. Compared to hydrochloric acid or sulfuric acid, carboxylic acids are very weak. That is true. Compared to an alcohol, they are relatively acidic. So here is an organic compound. This is the alcohol with the pKa of 16. However, the carboxylic acid, the corresponding carboxylic acid, is pKa of 4.76. The reason that it is so acidic for an organic compound is because that there's resonance structures. These bases are resonance stabilized. So you will easily recognize that. The equilibrium between the carboxylic acid and the carboxylate at physiological pH, which is 7.3, the acid and its conjugate base act as a buffer. Recall the Henderson-Hasselbalch equation here, which tells you that at psychological pH 7.3, the ratio of a carboxylate ion and the corresponding carboxylic acid can be calculated, and at physiological pH, that ratio is about 1,000 to 1 for the ion to the acid. So the carboxylic acids exist primarily as carboxylate salts at physiological pH. Indeed, pyruvic acid exists primarily as the pyruvate ion at physiological pH. So this is favored at physiological pH. Electron withdrawing substituents have a great effect on acidity. So here you can see a couple of trends. So the carboxylic acid, this is acetic acid, has a pKa of 4.8. If you put electron withdrawing groups on the carboxylic acid, it becomes more acidic, as you see by the pKa going to smaller numbers. And if you look notice here we have chloro going to the alpha position with one chlorine functionality being put on the alpha position. The pKa drops to 2.9. A second one reduces the pKa further to 1.3. A third chloro substituent at the alpha position reduces it further to 0.9. So as you increase the number of electron withdrawing groups, the pKa does indeed diminish, exactly as you would expect. That is because the electron density is being moved onto chloro. It's electron withdrawing. And so as it moves down onto chlorine, this is a through bond interaction. The electrons are being transferred through the sigma bonds. And so electrons are withdrawn, and the electron density that's in this oxygen-hydrogen bond is being pulled back off of the proton, and so the proton becomes bare of electron density, and it becomes very easy for it to just drop off. And so as you put on more electron withdrawing substituents, this oxygen-hydrogen bond pair of electrons moves more onto oxygen and into the molecule and off of the proton, and the proton becomes more acidic. And the third electron withdrawing substituent pulls the electron density off of the proton even more so. So there is the trend with regard to the number of electron withdrawing substituents. Now, let's look at another trend, and that is called the proximity effect. So when you have, let's compare a chloro substituent at the alpha position and compare it to a chloro substituent at the beta position versus at the gamma position. So you can see that as we go down this sequence, the chlorine is being moved farther and farther away from the carbonyl and the proton of the carboxylic acid. So as the chlorine moves farther away, you would expect it to have a reduced impact on the proton. And that is exactly what is observed. As the chlorine moves farther away, the pKa increases, and here when the chlorine is in the gamma position, the pKa of this molecule is 4.5, which is very close to the pKa of the molecule having no electron withdrawing groups at all. So you can see the proximity effect demonstrated nicely in these three molecules. Electron withdrawing substituents on the aromatic ring also affect the benzoic acid proton. So here all of these substituents are in the para position. And so you can see that as you go from electron withdrawing substituents to electron donating substituents, relative to a carbon-hydrogen bond here, relative to a proton, these electron withdrawing substituents pull electron density onto themselves and off of the oxygen-hydrogen bond, and so the molecule becomes more acidic, exactly as you would expect. This is shown by moving to a lower pKa. However, if one attaches electron donating substituents at that para position, and you compare the pH to that of the hydrogen at that position, just a simple benzoic acid, if you attach electron donating substituents, the electron density at this end of the molecule increases. And so one would expect the electron density in the oxygen-hydrogen bond to increase, and the electron density around that proton will increase. And so the OH bond will become stronger, and the proton is going to be covered in electron density more so, and so it will be harder or less likely for the proton to depart. And that means also, the other way to look at it is the stability of the corresponding anion, the carboxylate, which will be formed if the proton departs. It will not be so stable if electron density is being pumped in. And so you can see that the pKa is higher because this is less acidic. Now, preparation of carboxylic acids. You have had some preparations already. In section 9.9, we saw ozonolysis of alkynes leading to carboxylic acids, the oxidation of primary alcohols with strong oxidizing agents. We'll take this all the way to the carboxylic acid, that's in 12.10. The oxidation of alkyl benzenes. Remember, if you have an alkyl group attached which bears a proton, it must bear a proton, which this one does, then in the presence of a strong oxidizing agent, it will simply blast off any other alkyl groups and leave only that one sole carbon there, which is fully oxidized. We saw that in chapter 17.6. So that is purely review. Two more reactions. This reaction you have already seen, the hydrolysis of nitriles, the addition of dilute acid and application of heat will convert an alkyl cyanide to the carboxylic acid. So here you have an alkyl halide with treated with cyanide. So you have a SN2 reaction here. This anion will displace bromide. So now you have the cyano molecule, and so this nitrile is now hydrolyzed, and with the application of heat, so this is converted to the carboxylic acid. You've already seen this reaction previously. Carboxylation of the Grignard reagent. You've seen this also. The alkyl group will, the anion attacks the central carbon, which is bonded to two oxygens and therefore bears a slight partial positive. So the anion of the Grignard reagent attacks at carbon. Pair of electrons moves out onto oxygen. So here is the carboxylate that results, and then this simply picks up a proton to give you the carboxylic acid. this acid workup is necessary in order to neutralize the reaction, just as with any other Grignard reaction. So, this is the second method to convert an alkyl halide to a carboxylic acid in 2 steps. So you start with an alkyl halide, treat it with magnesium in ether. You have the Grignard reagent. The Grignard reagent then reacts with carbon dioxide to give you the carboxylic acid, just as you saw on the previous slide. Carboxylic acids, now we're looking at the reactions of carboxylic acids. They can be reduced to a primary alcohol. I think you saw this in the chapter on alcohols. So this reaction with the alcohol, with LaH, lithium aluminum hydride, the first step is that the lithium aluminum hydride, H minus, reacts with the H plus. Hydrogen gas will be evolved and will be left with the carboxylate. So this converts the carboxylic acid to the carboxylate. I might mention that this reaction will also occur with sodium borohydride. This reaction that I'm pointing at right now with the evolution of hydrogen will occur also with sodium borohydride. However, this next step, where the aluminum attacks the carboxylate, does not occur with the sodium borohydride. This step will not occur with sodium borohydride. And so you have H minus attack at the carbonyl, and the pair of electrons moves out to form an aluminum oxygen bond. Then the pair of electrons on oxygen moves in to form the carbonyl, and the leaving group departs. Then the aldehyde is reduced further with the lithium aluminum hydride. With the aldehyde, it is reduced further to give you the alcohol. And so this step does not happen with sodium borohydride. So normally lithium aluminum hydride can just be replaced by sodium borohydride, but not here. However, borane itself can be used instead of lithium aluminum hydride, and it is chemoselective for the carboxylic acid. So this will reduce the carboxylic acid to the alcohol. So if you have a molecule in which you have a carboxylic acid and an ester, using the borane, it will react with the carboxylic acid and not the ester. So that takes care of some of our reactions of carboxylic acids. So this is the end of lecture 2, and we will go on looking at additional reactions in the next lecture for carboxylic acids. We will look at forming some carboxylic acid derivatives and their reaction.